So this is example 4 continued. So hopefully we can finish this in one page. Let's have a look at the truss again. So we've already said that we want to work out what the deflection at that point is in the real system, and that means in the virtual system we should be putting a unit force onto there. Actually, we can put on any force, but in this case here, well, just to make your life easier, we might want to put a virtual force of 1 kilonewton. So I'll put the bar up there just to identify that it's a virtual force, but I won't bother putting the bars in the rest of the members. On the other side of the system, so we don't really care how far away the two trusses are, because that's not part of the question. We just want to get the relative movement. So we've got the truss on the other side. So we're putting 1 kilonewton there, or we're also putting this one bar of the kilonewton on that side there in the virtual system. So on the left hand side, let's just quickly work out what's happening. Firstly, if we take moments, well, if we took moments about that point, which would of course the same as taking moments about that point, so treating each truss separately, there's no need to treat them together, we get this 1 kilonewton. I'm not going to put the bar on top, but well, that would be the last time I'm going to put the bar, multiplied by 12 meters, 12 meters of course being the height of the system. And that is applying something in that direction, and so that must be equal to a moment in the other direction pushing it back, and that is going to be the reaction at B multiplied by 4 meters. Sorry, by 3 meters. So the reaction at B clearly must be going in that direction there, in order to have that in the opposite direction. So we've got the anti-clockwise moments must be equal to the clockwise moments, and then from there RB turns out to be 4 kilonewtons. So this 4 kilonewton acts upwards, and then down here, due to symmetry, we've also got another 4 kilonewtons acting upwards. And then that must be, obviously it should be 4 bars, but that's okay. And then obviously down here, that one is 4 kilonewtons downwards, and that's 4 kilonewtons downwards. So let's just go through the members. Since that's downwards, that member there must be in tension. Since that force there is going upwards, that member there must be in compression. Similarly, this member must also be in compression, this member must be in tension, this member must be in compression, and this member here must be in tension. So if you just wanted to identify which ones are tension and compression, just as a double check of your mathematics, that can be done. Now if you remember back to example 3, this 1 kilonewton was acting in the opposite direction, so here it's acting from right to left, but in the previous example acted from left to right. So we've actually already calculated all of the values before it, they just have to be reversed in sign. So this value here is minus 2.67, so kilonewtons, so look back to the previous one. This one here is minus 1.67, this one here is 1.67, this one here is 1.33, and then this one here is of course 4 kilonewtons. So and then if we just put the arrows in again, so we adopt our sign convention of tension equals positive, so we put tensile arrows everywhere, and where we have a negative sign, that obviously means that member is in compression. So let's put tension arrows everywhere, and the members that have turned out to be in compression are the three members on the outside and going round. So I've again circling just the members in compression, and that's minus 1.67. So if you don't know how to calculate those values, look back to example 3, where we had the 1 kilonewton virtual force acting in the opposite direction, which is why the signs have now been reversed. So now we're done. So let's go back to the equation. So we want to work out the delta of the real system, which would be the horizontal deflection of the real system, and that's going to be equal to the sum of n bars L divided by EA, and if we really wanted to, that's actually 1 times that's really that 1 kilonewton there. So remember, we've got a jack between those two members causing this 1 kilonewton. So this is the relative deflection that we're calculating. We could just consider either the left system or the right system and just double it, but just for argument's sake, or just for the sake of the explanation, let's just go through every single member in the whole system. So members 1 to 12, so same 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now, of course, remember that in the real system, a lot of these members have no load. So in the real system, let's just put N and kilonewtons, and that's the real system. Member 1 has 0, 0, minus 166.67, 0, 133.33, 0, 0, 0 up to member 9, which is minus 166.67, another 0, 133.33, and ending up down in zeros. So that's the real system, and then the virtual system, which is also going to be in the units of kilonewtons, as a result of this 1 kilonewton force applied to the system. Let's just put in the relevant numbers. So 1 minus 1, 1.67. The other one that's relevant is this 4. The other one that's relevant is therefore this minus 1.67. And again, we've got the 4 down here. So these are the members. These are the forces in the members that we've calculated in the members of the real system where the axial force was not 0. So let's now work out this n bar L. So a lot of the times we forget about this 1 kilonewton bar, but let's just be very precise with the units and say that's actually kilonewton squared times meters. So we work these two out, and we get 1389, and we get 2133, and then here we get 1389 by symmetry, and we get 2133. So of course we can see these two values are the same, and of course we can see these two values are the same. So the last step now is to sum those, and we get 7044, and that's obviously in units of kilonewtons squared times meters. So our change in tip separation, delta, change in tip separation is going to be equal to the n bars L over EA times your virtual 1 kilonewton force that you've applied. And remember, all of the n bars are proportional to the 1 kilonewton, so if we'd applied 10 kilonewtons, every member would have increased by a factor of 10. But that wouldn't change the answer, because you can see they would cancel each other out in the end. And then so we get 7044 that we've just calculated, divided by EA, which we calculated before, which was 1.6 times 10 to the 5 kilonewtons, So that's your EA multiplied by this virtual 1 kilonewton, and of course the units of that one are kilonewton squared meters, and the units of that one there are also kilonewtons, so we would expect an answer in terms of meters, and that answer then becomes 0.044 meters, which we'll say is further apart. So in the row system, which we'll just sketch out here, in the row system, your members would have moved apart. Would have moved apart by so it would have originally been apart there, been that distance there, and then it would have moved the sum of those two distances. So each of the two trusses would have moved 0.022 meters, and therefore 0.022 meters times 2 is 0.044, which is the distance that the two trusses would have moved apart. Now, let's just now complete the table, since we went to the trouble of working out all of those forces. 2.67 minus 1.67, 1.67, 1.33, 2.67, 1.67, 1.67, and 1.33, and since that's 0 times that member there, that's becomes 0, so all of these values would have been 0. And if we really wanted to, we could put the length of the members in. Well, obviously we should have done it for that one which we knew to be 5, and that member length which we knew to be 4, and that member 5, and that member 4, because obviously we used that when we calculated that, so I should have added that in right at the start. And then if we really wanted to, all the other values, 8, 8, 5, 5, 5, 4, and 8. But as you can see, we only needed to actually work out member 3 and member 5, and we also actually only did member 9 and member 11, which is the same as members 3 and 5. So actually we didn't have to calculate all of those, all of the values of the all of the axial forces in the truss. We just needed to concentrate on members 3 and 5.